So welcome to Server Farm to Table, in which I teach you about how the internet works in 25 minutes. All right, so I'm going to need some help from some friends. So meet client and web server. Yeah, so as Jen mentioned, I'm an engineering manager at DigitalOcean. This shark is Sammy. Sammy really likes their dinosaur costume. So you might have gotten a sticker that looks like that outside. If you want one, you haven't gotten one, come talk to me. I want to make some friends. Figured stickers would be good bait. And speaking of alter egos, you might know me as Zeigen Vector on the internet, so feel free to tweet at me if you have any questions. I'll also tweet these slides a little bit later after I'm done being on stage. All right, so you might have been asked once or twice, what happens when you type www.google.com into the browser and hit enter? Well, it's these things. So I'm going to go through all of these and talk about some optimizations that we can do along the way to make our websites super fast. All right, so the first thing that happens is your computer needs to map the human-readable URL www.google.com to the address of a computer to talk to. And that is going to be your IP address, or the IP address of the server you're trying to talk to. So the first thing that's going to happen is the browser is going to check its cache. Now, spoiler alert, caching is going to be a very popular topic throughout this entire talk. I'm going to mention a bunch of the places where it happens along the way, but we're going to assume that it never works, or else this would be a very short and boring talk. So assuming that the browser does not have this IP address in its cache, it's going to call the getHostByName library function to do this lookup. And getHostByName is going to check if this host name is listed in the local hosts file. So on Macs, I happen to know that this file is located at /etc/hosts. And fun fact, this is how your computer knows what localhost should resolve to. So you could theoretically change that in your host file, but I wouldn't recommend it because who knows what would break. So if getHostByName does not have the IP address cached and it can't find it in the local host file, it's going to make a request to the local DNS server, which is typically your internet service provider, your ISP's DNS server, but you could tell your computer to use whatever DNS server you wanted, such as Google's, which I happen to know is at 8.8.8.8. So then the browser is going to send off the request to the DNS server to get www.google.com, which is going to go through the local router, which is also going to check its cache for you. Why not? And Jed Schmidt calls this the landsplaining slide, so thanks, Jed, for that joke. So if the local router doesn't have anything cached, the request is going to go right on through, and it'll hit the DNS server. And this request is going to be using UDP, which is the User Datagram Protocol. And a brief explanation of UDP, it's kind of like the lowest level Pokemon of internet protocols. It's great for unidirectional transactions, but delivery isn't really guaranteed in any order or guaranteed at all. So it's kind of like if you're just throwing a bunch of frisbees at someone on a really windy day, there's that you might not be very great at throwing the frisbees, they probably won't end up catching them, they're probably going to end up going everywhere. They might catch one or two, but no guarantees. So when the DNS server receives the request, it's going to check its cache. And assuming that it doesn't have it in its cache, it's going to end up recursively looking up the address by recursively asking a bunch of other server friends. So meanwhile, the client then has to wait for the answer. So that DNS server is first going to be like, hey, root name server, do you know where www.google.com is? And root name server is going to be like, no, but you should go ask our friend.com. And then DNS server is going to be like, hey, .com, do you know where www.google.com is? And .com is going to be like, nope, but maybe you should go ask google.com. And then DNS server is going to be like, all right, google.com, do you know where www.google.com is? And then google.com name server is going to be like, yep, it's right there. And then the DNS server will cache the answer for an amount of time specified in that response from this name server. And then the DNS server will report back to your computer, and your computer is going to cache it. If you like your terminal and you want to check this out in a little bit more detail, you can use the dig command. All right, so once you have that IP address, your computer is going to take that address and the given port number from the URL, and it's going to make a call to the system library function named socket and request a TCP socket stream. And when you're casually browsing the internet, you don't usually see port numbers at the end of URLs. That's because the HTTP protocol has defaults. So HTTP is going to default to port 80, and HTTPS, the secure one, is going to default to port 443. And so TCP is the transmission control protocol. Its job is to deliver a reliable, ordered, and error-checked stream of packets across the network. And TCP is very important to the internet as we know it today because it's what underlies HTTP, TLS, which we'll talk about in a bit, as well as FTP, email, and SSH. So many important things. So the client is then going to establish this TCP connection with the web server. And it's going to look something like this. So client's going to say, hey, will you talk to me? Web server is going to be like, sure. And then your client's going to be like, awesome. It looks more technically slightly like this. The computer is going to send off a SYN packet with some information. The server is going to send back a SYN-ACK packet with the derivation of the first bit of information and some new information. And then your client's going to send back a ACK packet with derivation of the second bit of information as well as a repeat of some of the middle bit of information. There's a lot of information. And so something cool, or at least kind of planning for the future about TCP in this case is more than one connection is going to be opened. And the extra ones are going to be saved for later. Something that's also important, though, kind of like a relic from the past about TCP is TCP has congestion control. So the requests are going to start small and ramp up in size to make sure that the network can support the requests, because this was from back in the day when networks weren't so reliable. So we wanted to make sure that all that important information was received and accounted for. So TCP is where a lot of the latency comes from in the internet, because TCP, like many things, is constrained by the speed of light. So the distance between computers plays a fairly significant role in how fast these transactions are going to occur. And this is one of the great things about CDNs, is you can put your assets as close to your users as humanly possible. So if you like your terminal and you want to check out more about TCP, you can use TCP dump. It apparently also catches UDP. All right, so should you want this whole thing to be secure, and I highly recommend it, you're going to want to use TLS, which is Transport Layer Security, and its predecessor was Secure Sockets Layer, or SSL. So I don't know very much about this, so I'm going to gloss over it. Also, I only have 25 minutes. So, So TLS is also a handshake, but it is more complicated than the TCP handshake. So the first thing that's going to happen is client's going to be like, client hello, and here's some info. It's going to send that to the server, and then the server is going to reply with a server hello message with some other info, and then they're going to exchange some secret messages, do some cryptography stuff, and then agree that the whole conversation is finished. So once everything is all nice and secure, then we can get on to HTTP. So HTTP stands for Hypertext Transfer Protocol. So unless the client and server negotiate using a more recent version, we're going to be using HTTP 1.1. It's pretty much what most things are still using now, so we're going to talk about that. So the client is going to send a request that looks something like this, containing the request, and then some headers, and then a single blank new line to the server indicating that the content of the request is done. And then the server is going to receive that request and process it using an HTTP daemon, and examples of this are Apache and Nginx. And I'm a front-end engineer by training, so this is what I think servers do. They might do some load balancing, some database stuff, there might be some magical unicorns, and then they will process the request. So the server is going to break down the request using, to get the following parameters. So it'll get the HTTP request method, which is either get, post, head, put, delete options. In this case, because we entered a URL directly into the address bar and hit enter, it's going to be a get request. It will also suss out the domain from the request, which in this case is google.com, as well as the requested path or page, which in this case is / because no specific page or path was requested, and / is the default path, just like in the Unix file system. So then the server will send back a response. So if you've been to the site before and your computer cached it, and the HTTP headers sent by the web browser included enough information for the server to determine that the cached version is indeed the latest version, it may respond with something like this. This has to be set up ahead of time, so hopefully it is. But at the rate that y'all are developing these days, it's likely there's going to be a cache miss, which means that the server is going to send the whole thing on over again. So successful requesting and servering will prompt the server to send everything on over in a response that looks something like this. So you'll get a 200 OK status code, a single blank new line, and then, in this case, the entire HTML payload. And I kind of glossed over headers a little bit, but headers are essential for making sure that this client-server conversation works. So I implore you to look up more about the cool things that headers help computers talk to each other about. In the sad case that there was not successful requesting and servering, you could also get less happy things, like a 400 series error, that's if the client did something wrong, or a 500 series error if the server did something wrong. So in the wild, you can use curl to get HTTP responses and look at them. So yeah, so this is just google.com. So it's a lot for such a simple website, right? Relatedly, the size of the request is directly related to how long it takes to finish the request. So you want your responses to be as small as possible, because smaller is often better. So gzip is a very popular compression method, and it's great for HTML because of the way that it works. So the way that gzip works is it takes repeated substrings and replaces them with references instead, so you don't have repeated information throughout your document. And this generally reduces the response rate, the response size by 70%, which is pretty big. So use gzip or some other compression method. So as soon as the browser starts receiving bytes, it's going to start parsing it. And it's going to usually receive the bytes receive the data in 8K chunks. So before the formal parsing for rendering, the bytes are going to get passed through a speculative or look-ahead pre-parser. And the job of this parser is to look ahead for external resources. So that's your JavaScript, your CSS, your images. So it can start getting them from the server immediately. So if it finds these external resources, it's going to use the extra TCP requests that I mentioned earlier if these things are being served from the same host. Otherwise, the client has to do the whole DNS dance again. So meanwhile, the bytes are going to get fed into the primary parser. And the parsing algorithm for HTML is described in great detail in the spec. I haven't read it, though. So in short, the browser is going to read the raw bytes of HTML and translate them into individual characters based on the specified encoding, like UTF-8. And then the characters are going to get broken up into tags, which are then made into nodes, which are then arranged in a DOM tree. So you're going to end up with the DOM tree. DOM stands for Document Object Model. And the element in the tree generally have a one-to-one relationship to the markup. So unlike most parsers, the HTML parser is not context-free because the HTML spec requires that HTML be very forgiving. So in fact, the parser is supposed to be 100% fault tolerant, which is why you never see an HTML syntax error. Did you ever notice that? So a lot of the code that goes into the parser is dedicated to fixing the HTML author mistakes. So it has to put all the, add in closing tags, etc. So browsers are really big. There are like a million lines of C++ or whatever, and a big chunk is related to making this magic happen and fixing our stupid human mistakes. All right, so again, parsing the HTML, blah, 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 and then the client has to request and parse and execute all of the inline assets and scripts. So again, the size of these things is going to directly correlate to how long it's going to take to download them. So you should probably be gzipping or compressing, minifying all your CSS and JavaScript and optimize your images. So something that we have to work around is that browsers have imposed limits on how many parallel downloads you can have from the same domain. So back in the olden days, it used to be 2, and now it's anywhere from 6 to 13, last time I checked. Regardless of how many, this is a bottleneck. So something you can do to get around this is to serve your assets from multiple host names, which is yet another benefit of a CDN. Another thing you can do is combine your files together, so concatenate your JavaScript and CSS, make CSS sprites, etc. Caching also helps here because files that don't need to be downloaded don't contribute to the download limit. All right, so as the parser is going through and it runs into a JavaScript include, further parsing is going to stop. So you might have heard like JavaScript is blocking. And this is because JavaScript has the ability to manipulate the DOM using our favorite method, document.write. So any HTML that gets added must then be fed back into the main parser. So the parsing of the document is going to halt until the script has been downloaded, if necessary, and executed. And while the script is downloading, the browser won't start any other downloads, even on different host names. So this is one more win for concatenating and minifying your JavaScript, and it also explains the script at the bottom of the page optimization. So you want to put your JavaScript, if possible, right before the closing body tag. So when the blocking happens, all of the good things have already happened. So to get around this, you could maybe add a defer attribute to your script, in which case it will not halt document parsing and will execute after the document is parsed. Or more recently added, you could put in this async attribute, which signals to the browser that this document, that this JavaScript should be parsed and executed in a different thread in parallel. But it's kind of like a promise that you won't call document.write. So CSS is actually blocking as well. So the browser is going to delay script execution until it has finished downloading and parsing the CSS. And DOM construction is also going to be blocked. Why is this? Well, let's take a look at the CSS parsing process to see if we can figure anything out. So just like with HTML, the browser needs to convert the CSS file into something it can work with, which is the CSS object model, or CSS-OM, as I like to call it. So the CSS parser, unlike the HTML parser, is indeed context-free, though the steps in the process are largely the same. So you're going to end up with a tree. And the tree makes sense because of the recursive nature of style application, or the proverbial cascade. And the CSS-OM is only going to include overrides to the browser's default style sheet. So only things that you've explicitly added to say what you want your page to look like. So I mentioned that JavaScript can read and modify the DOM, but it can also read and modify the CSS-OM. So this is why it makes sense that JavaScript shouldn't be executed, because it's going to want all of the information, so it's not doing something incorrect. So once the CSS-OM is made, the JavaScript files can continue to be parsed and executed, and so on and so forth, until we reach the end of the HTML document. But we're not even close to being done yet, because there's nothing on the page yet. So the CSS-OM and DOM trees are combined into a render tree, which is then used to compute the layout of each visible element and serves as an input to the paint process. So this is going to render the pixels to the screen. So because of this, HTML and CSS are both render blocking resources. So the browser is going to hold off rendering anything until both the DOM and CSS object model trees are constructed. So this, in addition to CSS blocking JavaScript, is why it's a good idea to put your style sheets at the top of the page. So putting style sheets near the top is going to putting style sheets near the bottom is going to prohibit progressive rendering in many browsers. So these browsers are going to block rendering to avoid having to redraw elements as their styles change. And if this isn't enough, the HTML spec states the style sheet should go in the head. So there's your reason. So elements in the render tree are going to correspond to elements in the DOM tree, but it's not necessarily a one-to-one relationship. The render tree is only going to include things that are supposed to be rendered. So there's not going to be any script tags in there or any non-visual DOM elements. So nothing like display. Just visibility hidden things will be in there because it leaves space for it, right? All right, so while the render tree contains information about what nodes are visible and computed styles, we don't yet know where these things are going to go or how big they're supposed to be. The process of figuring this all out is called layout. And layout is a recursive process, so it's going to start at the root renderer, which corresponds to the HTML element of the document, and it's going to continue computing the geometric information for each renderer that requires it. And all renderers are going to have a layout method, and then each renderer is going to invoke the layout method of its children that need layouts. This is a recursive process. So in order to not do a full layout for every small change, browsers are going to use a dirty bit system. And the renderer that is changed is going to mark itself and its children as dirty or needing layout. So there are two flags, dirty or its children are dirty, which is that even if the renderer itself is okay, it has at least one child that needs to be relayed out. And so layout can be either global or incremental, and incremental layouts are done in async batches based on a timer in the browser. So once we know where these elements are supposed to go and how big they're supposed to be, we can start representing them as pixels on the page, which is, important. And this is called the painting process. And in the painting stage, the render tree is traversed again, and the renderer's paint method is called to display the content. So like layout, painting can also be global or incremental. So then in the incremental process, only dirty regions are repainted. This is how we get that much coveted region-specific repainting. So when the HTML document is fully downloaded and parsed, the page is marked as interactive and the DOM content loaded event is fired. So not all assets have to have been downloaded or processed for the event to be fired, but at this point you can click around the page. It's interactive. Also at this point, scripts marked as deferred are going to be executed. And then finally, once everything has been downloaded and parsed, the document is marked as complete and the load event is fired. We're done. Almost. There's this. I mentioned when we started on this HTTP journey that we're going to be using HTTP 1.1, but there's a new thing, it's HTTP 2, and this grew out of the work that Google did on this thing called Speedy, because all those optimizations I talked about, they're to smooth over things that don't work so well in this whole process. And HTTP 2 endeavors to fix all those things. So a lot of the performance tricks I just talked about won't be necessary anymore when the whole world is on HTTP 2, whenever that is. So that'll be good. All right, so we talked about a lot of things, these things. And if you want to learn more about any of these, here's some resources. There's some resources that I used to make this. And if you're interested in what songs I butchered, these are them. So if you want to find these slides, they're at that link. And this is actually an abridged version of a talk I gave before. Also, it's like, you can't explain the whole internet in 25 minutes. So there's a longer version with like speaker notes written in complete sentences at the longer link. So thank you for listening. I hope you enjoyed it, and feel free to tweet at me or find me in the hallway track if you have any questions. Thanks.
So if you want to learn how the internet works, what is like a good resource to start? Because like your slides were really awesome. Like all the tweets coming in are talking about how like great the hand-drawn stuff is, cool. and the songs and stuff like that. And being a visual person, it's hard for me to like read like very verbose documentation. Are there any really good resources for learning this kind of stuff that's not gonna make me want to take a nap every time I open it?
Well, this video is going to be on the internet, right? The thing that got me to really understand all this was actually a talk I saw before. Other than that, it was pretty much just like reading a lot on the internet. Sorry, I don't have any good answers for you. There is a GitHub repo that has a bunch of this, but it's even more minutiae than what I just presented. It even goes into like even lower level, like what happens when you like push the key and it bottoms out. Like stuff you didn't even know that you didn't know how it works.
Yeah, it's really crazy because like you went through that whole list, and that's really all that happens to like access like Google.com,
Yeah.
for example. So there's like a lot going on in the back. It seems incredibly inefficient, if you ask me. But what I find interesting about it, and why I feel like this kind of stuff is important to learn, even just like as people who are building for the web, like you don't need to know about HTTP really in order to just like get a page online. Usually that work is delegated to other people. But I feel like with all of the latest in terms of like net neutrality, I feel like it's really important to learn this kind of stuff. Just learning how like internet service providers are like forging packets to slow down sites for some people. And another thing, like you were talking about like the needs to optimize your code so that things are faster. What are some other things that like you learned or that you now think of when you're building for the web, now that you know all this stuff?
I do need to learn more about how the whole rendering and painting process works. I think especially for front-end engineers who are trying to make cool things look really cool and they make cool animations, you need to know how that painting process works. Like request animation frame works that way for a reason, and it's good to know why. Yeah.
Painter's gonna paint.
Painter's gonna paint. Renderer's gonna rend.
Awesome. Thank you so much.